Let's do an example problem involving rotational kinetic energy. So in this problem we have a solid cylinder with a mass of 3 kilograms and a radius of 0.2 meters starting from rest at the top of a ramp inclined 15 degrees, and then it rolls to the bottom without slipping. The upper end of the ramp is 1.2 meters higher than the lower end, and we want to find the linear speed of the cylinder when it reaches the bottom of the ramp. So let's draw a picture of this. So we have this inclined ramp. The ramp is inclined at an angle of 15 degrees. And we know that the ramp has a height at its highest end of 1.2 meters. And there we have this cylinder, and it's a solid cylinder that starts at the top and then rolls down to the bottom. Now, we are given some facts about the cylinder. We're told that it is 0.2 meters and it has a mass of 3 kilograms. So we can use that information to figure out the moment of inertia of the cylinder. So the moment of inertia of the cylinder, since this is a solid cylinder, it would be 1/2 times mr squared. So that's going to be equal to 1/2 times the mass of 3 kilograms times the radius of the cylinder, which is 0.2 meters, and that gets squared. So the moment of inertia of this cylinder is 0.06 kilograms times meters squared. So we have the cylinder's moment of inertia. All right, so we want to find the linear speed of the cylinder when it reaches the bottom of the ramp. And we have the cylinder rolling down the ramp. So this sounds to me like a problem that we can use conservation of mechanical energy for. We have some potential energy when the cylinder's at the top, and then that potential energy turns into kinetic energy as the cylinder rolls down the ramp. So since the cylinder is rolling, we have to consider both rotational and linear kinetic energy. So we can write down a conservation of energy expression. So that would look like mgy initial for the initial potential energy plus 1/2 m times v initial squared. So that's the ordinary linear kinetic energy plus 1/2 I omega initial squared. There's our rotational kinetic energy, is equal to the same quantities in the final scenario when the cylinder's at the bottom. So that would be mgy final plus 1/2 mv final squared plus 1/2 I omega final squared. So just as we did before with this kind of conservation of energy problem, it's convenient to next look and see if any of these energies are equal to 0 so we can simplify things. So if I want to decide where the potential energy is equal to 0, I have to figure out where my y equals 0 height is. And I think I'll put it down at the bottom of the ramp. So this is where y is equal to 0. I could choose to put it up here as well. It doesn't matter. So, but I think I'll choose it to be the bottom of the ramp. So this is y equals 0. So that means that my y final here is going to be equal to 0, since that's where the cylinder ends up. So the final height of the cylinder is 0. So this term is going to be 0. The initial height then is going to be 1.2 meters, so that will not be 0. Then if I think about the motion of this cylinder, I'm told that it starts from rest. So if it starts from rest, its initial velocity is going to be 0, so this term is 0. And if it starts from rest, it's not rotating either, so its initial rotational kinetic energy is also going to be equal to 0. But it will have some final velocity and some final rotational speed as well. So then let's equate the non-zero terms, mgy initial is equal to 1/2 mv final squared plus 1/2 I omega final squared. All right, so let's look at this more closely. I know what the mass is, and I know what g is. I know what the initial height of the cylinder is. So I have all of those terms. I know what mass is. V final is the thing I'm trying to find. I want to know what is that linear speed when it reaches the bottom of the ramp. I know what I is. So what about omega final? So this is the final rotational velocity of the cylinder when it reaches the bottom of the ramp. How fast is it spinning? Well, there's a key phrase in this problem, and that is that the cylinder rolls without slipping. It rolls to the bottom without slipping. So if it's rolling without slipping, then that means that each point of the cylinder as it touches the ground or touches the ramp does not slide, and so you can equate the speed of the cylinder at the bottom where it's touching the ramp. You can equate how fast that's moving along with how fast the cylinder is rotating. So in fact, you can write down that V is equal to R omega. This is the no slip condition. So since that is true, then that means that the final velocity is equal to r, the radius of the cylinder, times its final angular velocity. And if I solve for omega final is going to be equal to v final divided by r. So then I can put this expression in place of omega final. So mgy initial is equal to 1/2 mv final squared plus 1/2 I times v final over r squared. And remember that v final, that's the thing I want to learn about. I want to know what is that final velocity. So the next thing I can do is distribute the squared over these parentheses. So I get mgy initial is equal to 1/2 mv final squared plus 1/2 I times v final squared divided by r squared. And then I can factor out the v final squared from these two terms. So that's equal to 1/2 mass v final squared. Oops, I did that a little bit backwards. It's the v final squared I'm going to be factoring out. So v final squared is equal to 1/2 mass plus 1/2 I divided by r squared. And then that's going to be equal to mgy initial. So then my v final squared will be equal to mgy initial divided by 1/2 mass plus 1/2 I over r squared. And then I can just take the square root of both sides to get my v final. So putting in some numbers, that's going to be equal to the mass, which is 3 kilograms, times g, 9.8 meters per second squared, times the initial height, which is 1.2 meters. And then that gets divided by 1/2 times 3 kilograms plus the moment of inertia, which is equal to 0.06 kilograms times meters squared. There is a factor of 2, and also an r squared, where r is the radius and the radius is 0.2 meters squared. So then that's going to give me an expression that's equal to about 3.96 meters per second. So the cylinder will be traveling 3.96 meters per second once it gets to the bottom of the ramp.